Welcome to our first of 3 review lectures being prepared for the final exam. We've covered a lot of material. The final exam is cumulative over the semester, because the hope is that you've learned something this semester, that you now know this material. So if you are teaching, let's say, 3rd grade science class, you can use this in your teaching. So chapter 0 was the prologue, which gave us an overview of what physical science is. So for instance, this first review is just covering physics. The second review will be chemistry, because that was exam 1 and exam 2. And then the third review will be earth science, meteorology, and astronomy. In chapter 0, not only do we lay those out, but we have the scientific method, and you will have essentially the same scientific method question you had in the first exam. It will have a different observation, but it will still be, you will have to list these 4 steps. So make sure you have these memorized, because you have to just regurgitate that. Then you will have an observation that I will give you, and you'll have to say step 1, and you'll have to restate that observation. Step 2, and you'll have to state a hypothesis that you can make based on the observation and based on scientific ideas that fits those 3 criteria. Step 3 is you will describe the test you'll make and the outcome that would agree with your hypothesis, the outcome that would disprove it. And 4, you give if outcome A, then, and if outcome B, then, where outcome A and outcome B are based on your hypothesis. So you don't say if outcome A, it's based on your hypothesis. So make sure you have that memorized, because that's going to be, once again, a significant fraction of the points in the test. Then chapter 1, we start in with physics, and we were looking at motion. So make sure you know the difference between Aristotelian thought. Aristotle thought that there were just natural motions. The natural position for something was to be on the ground if it was made of earth, to be sitting on top of the ground if it was water, to be on top of water if it was air, and to be up to the top above air if it was fire. And so things did whatever they did based on how much of these elements they had. Whereas Galileo said, no, the natural motion is just to stay in constant motion. That means constant velocity. That means constant speed and direction. And Galileo believed in testing things. So we have his, dropping 2 objects off of the Leaning Tower of Pisa and seeing which hits the ground first. And what Galileo said was they should reach the ground at the same time, because even though the bigger one has more earth and Aristotle said it should go faster, it's not that. Now, inertia is measured in units of mass, that is kilograms, and it's the resistance to change in motion. We have Newton's first law, that'll be on another slide, that says, it's called the law of inertia. It says an object in motion stays in constant motion, that's inertia, unless acted on by a force. And then the second law tells you how inertia works. It tells you the net acceleration is equal to, as the acceleration of the object, is equal to the net force acting on the object divided by its mass. And we'll have those on a slide coming up. Forces, anything that pushes or pulls. Make sure you know that. Forces, anything that pushes or pulls. And common forces that we've looked at, friction, which depends on the normal force. Normal or support force, the force that keeps an object from going into a surface, so it's always pointing out of the surface, the so-called normal direction. Gravity, an attractive force between any 2 objects with mass. Tension, a force that's distributed over some kind of cord or chain or something. Equilibrium means equal forces. And so make sure you can solve equilibrium problems. So, the typical equilibrium problem is like, we have this hanging platform, and we have a man here, and we have a woman here, and we have the mass of the source is here. And if you have the mass of the man, the mass of the woman, the mass of the plank, and you know their positions, then you should be able to calculate what the tension is on each side of the rope. Well, that was beautiful. Make sure that you can distinguish between speed and velocity. Velocity has direction, speed doesn't. Both of them are the rate at which position is changing. So both speed and velocity change in position over change in time. But velocity, we put an arrow over it and it has direction. And acceleration is the rate at which velocity is changing. And of course, you should know that these triangles are the Greek letter delta, and they mean change in, which is final value minus initial. Newton's law, the first law, the law of inertia, already talked about. Object in motion stays in motion unless acted on by force. Second law, we usually write it like this, or the textbook prefers this. They're the same thing. Net force and sum of the forces mean the same thing. And so for an object with mass m, its acceleration depends on the net force acting on it. And so you should be able to use this in simple cases. The third law, equal and opposite forces. What that's saying is if I have an object here and I apply a force of 1 on 2, then the other object is going to return a force of 2 on 1, that is equal in magnitude but opposite in direction from force 1, 2. So like I said in class, if you punch a wall, that wall puts an equal and opposite force on your fist. And if your fist is stronger than the wall, then the wall breaks. If the wall is stronger than your fist, then your fist breaks. So make sure you know those laws and can use them. Let's just do a simple example. Let's say we have a box here, and we have a person pushing with force push equals 10 newtons, and the box has a mass equal to 5 kilograms, and the force of friction is equal to 2 newtons. Well, then if I want to find the acceleration, the sum of the forces, so I'm going to have to decide to the right is positive. And so I'm going to put the sum of the forces is 10 newtons to the right minus 2 newtons to the right, because it's actually 2 newtons to the left, all divided by that mass of 5 kilograms. And so that's 8 newtons over 5 kilograms equals 1.6 meters per second squared. So you should be able to do that kind of problem. Chapter 3, we looked at momentum and energy. So momentum, symbol P, is equal to mass times velocity. And since net force is equal to mass times acceleration, but acceleration is change in velocity over change in time, then I can combine the mass and velocity so that net force is change in momentum over change in time. So if the net force on a pair of objects is 0, then the momentum won't change. So we did a lab on this where we had a, quote, frictionless, end quote, track, and so momentum should have been conserved. So know the condition where momentum is conserved and when it's not. And impulse, if we take this equation that I just wrote and we multiply everything by delta t, we get the net force multiplied by delta t is equal to the change in momentum. And we call this side here the impulse. So the impulse is equal to the change in momentum, but it's net force multiplied by the time over which that force acts. So you should be able to solve some conservation of momentum problems. Remember that in collisions, we had 2 types of collisions, elastic and inelastic. And those had to do with energy. So we have to talk about energy before we can really talk about those. So make sure that you know that work is equal to force times the distance parallel to that force. And work then is something that is a force that's making something move. So if I stand on the ground, I'm putting a force on the ground, but I'm not making it move, so I'm not doing any work. But if I push on the car and the car moves, then I'm doing work on the car because my force is making it move. So you should be able to calculate work. And then we had the work energy relationship that said change in kinetic energy is equal to the net work, which of course would be force net times distance moved parallel to that force. So kinetic energy is the ability to do work because of motion. And it has an equation, kinetic energy is equal to 1/2 mass times speed squared, or if you put it in terms of momentum, momentum squared over 2m. So we have kinetic energy, energy in motion. We also have potential energy, which is energy based on position. So we have things like potential energy due to gravity was mass times acceleration of gravity times the elevation. Or we have the potential energy in a spring was equal to 1/2 the spring constant times the amount the spring is stretched squared. So potential energy is energy based on position. It's still ability to do work, but it's ability to do work because of position or configuration. So with the collisions, elastic collisions were collisions that conserved kinetic energy, whereas inelastic kinetic energy decreased. Kinetic energy was transformed into some other type of energy. We have the conservation of momentum that occurs only if the net force is zero. We have conservation of energy always. Total energy is always conserved. You can't create or destroy energy, but you can move it from one type to another. So remember the example with the bowling ball. Bring it up to my chin, let it go. It initially started with all potential energy, gravitational potential energy. But that gravitational force did work on the ball, converting gravitational potential energy into kinetic energy. So at the lowest part of its swing, it was all kinetic energy. But then that kinetic energy did work on the ball to put energy back into potential energy. And because energy is conserved, in theory, you would have thought, oh, it should just come up to the same height that I dropped it from. But in practice, some energy was converted into moving air. And so it lost a little bit of energy, little energy in the bowling ball went away, went into the air. It wasn't destroyed, it wasn't lost from the earth. It simply went into a different form of energy instead of being in the bowling ball. Now with gravity, we had that universal law of gravity. The force of gravity equals G mass 1 mass 2 over the separation squared. We also had learned force of gravity is equal to mg. This form here we use on Earth, where mass 1 is equal to the mass of the Earth, and d is equal to the radius of the Earth. And so that lowercase g is just capital G times mass 1 over d squared. And then mass 2 is this mass we had there. So they're really fundamentally the same equation, but the one that I drew above the title here is only usable on the surface of the Earth, where we have an approximately constant separation from the center of the Earth. Weight is generally defined as the force of gravity acting on you. So our textbook actually says W equals. I don't use W there because W also stands for work, and I don't want to confuse things. So I just erased it after writing that. But that's generally what we describe weight. But then weightlessness gets confused because weightlessness is when you have no normal force. So probably a better way of identifying weight is what's the normal force if you're standing stationary. Weightlessness is when you fall under the influence of gravity with nothing else affecting you. So weightlessness is when you're in free fall. So if you are in an elevator and the elevator is falling, and of course we have all kinds of safety things so this can't happen, but if you're in an elevator and it's falling, then you're weightless. If you were to put a scale underneath you, you wouldn't weigh anything because you wouldn't be pushing down on that scale. In the same manner, if you were in the International Space Station, where the force of gravity is somewhere like 80 to 90% what it is on Earth, I mean, it's still a significant amount, but that International Space Station is falling at the same rate that you are, and so you feel weightless. Projectile trajectories. We have the horizontal motion that we calculate using x final equals x initial plus v x initial t plus 1/2 a x t squared, where we usually use x to be horizontal, y to be vertical. The same equation can be used in the vertical direction, and the vertical and the horizontal directions are completely independent, but the acceleration is only in the vertical direction with the value of g. So with trajectories, because the acceleration in the horizontal direction is 0, then this is 0 for the x direction, but for the y direction, it's not. Y. So here I substituted g for the acceleration in the y direction. So you have those two equations to give you position as a function of time. You also have the velocity is equal to the velocity initial plus acceleration times time, and you can put that in the x or y direction. So I'll put y here. So those are what we call kinematic equations that we use to describe motion. So you should be able to calculate the acceleration if something has a constant acceleration and you have the initial and final speeds and the time, or if you have the initial and final positions and the initial speed. We often set the initial speed to 0 to make your calculations easier. So you should be able to manipulate those equations for trajectories. Now, escape velocity, that's not a really big thing for us to know, but escape velocity is when you have enough kinetic energy to convert all of your kinetic energy into potential energy and get away from the Earth and still have a little kinetic energy left. When you have something orbiting the Earth, like the moon, for instance, here's the Earth, and here's the moon. The moon has a force of gravity that's pulling it toward the Earth, but it has a velocity that is tangential, perpendicular to the line going from the moon to the Earth. And so it's constantly being accelerated toward the Earth, but it's actually making it go in a circle. If in this case we say that acceleration toward the center is equal to the speed squared divided by the radius, if it's doing a circle. Now that's if it's doing a circle. Actual orbits are elliptical. So for instance, our last chapter was on astronomy. We have things like comets that orbit the sun. And some of these comets have very eccentric orbits like this. And so they're elliptical in shape, not circular. Even the planets are somewhat elliptical, but not to this degree. And they go slow out here, and they go really fast when they're close to the sun. Then we got to fluids. Now, in fluids, we had density. Rho is the symbol for density, and it's mass divided by volume. So different types of materials have different densities. That is, for the same volume, you might have more mass or less mass. Make sure you understand what mass is, a measurement of how much matter is present. We also had pressure. Pressure is equal to the force divided by area. The force is always going to be in the direction pointing into a surface. So if I have a cup and that cup is filled with water, I probably should have made the water blue instead of the cup blue, then that water is going to put a force on the sides, and everywhere it's pushing into the surface. And if we take this equation, that force is equal to pressure times area. Now the pressure increases with depth. So here at the top, we have what we call the atmospheric pressure, which is equal to pressure that's due to the weight of all the air above us. And then as you go down the water, the density of the water makes it so you have more weight above. And so you have the pressure difference. So I'm going to put delta P pressure difference from the atmospheric pressure, is equal to the density of the water times the acceleration of gravity multiplied by the depth of the water. So D is the depth. So the pressure is increasing as you go down further. Archimedes' principle was that the buoyant force is equal to the weight of displaced fluid. Now, weight we learned was mg, but since density is mass over volume, then mass is equal to density multiplied by volume. So that's equal to density times volume times g. That's the density of the fluid and the volume displaced. I'm going to erase the parenthesis now. Maybe. There we go. And so that's what the buoyant force is. The buoyant force is the upward force that's the net force caused by pressure in the fluid pushing in on an object. So if I have, here now I'm using the right color scheme. So if I have an object in here, I have water pressure that's pushing down on the top, pushing up on the bottom, pushing in on the sides. The sides are going to oppose each other, so those are going to add up to zero. But the bottom is going to be a bigger force because it has a bigger pressure, and it's the difference in those that gives us the buoyant force. Now, the final thing here in fluid mechanics is Bernoulli's principle. Bernoulli's principle says that faster flowing air has a lower pressure. So we have pressure 1 plus 1/2 rho of my fluid V1 squared plus rho of my fluid GH1 equals pressure 2 plus 1/2 rho of my fluid V2 squared plus rho of my fluid GH2. That's the actual equation for Bernoulli's principle. What you really need to know is faster flowing fluid, lower pressure. So when you have very high winds, that makes the air pressure lower. So your house is trying to push the walls and ceiling off because you have higher pressure inside and lower pressure outside. Chapter 6, thermal energy and thermodynamics. So it's important to know the difference. Well, know what heat is. Heat is a transfer of energy. So I can be hot, but I don't contain heat. I contain thermal energy. And heat is a transfer of that. So when I am being heated up, there's energy going into my body. When I am cooling down, heat is going out of my body, energy is leaving my body. Temperature, on the other hand, is a measurement proportional to average kinetic energy, proportional to average kinetic energy of the molecules. So at higher temperature, the molecules are moving faster. They have a higher kinetic energy. At lower temperature, they're moving more slowly. Now we have 4 laws of thermodynamics. The 0th one, if temperature 1 equals temperature 2 and temperature 2 equals temperature 3, then temperature 1 equals temperature 3. It seems really obvious. So nobody thought to make that a law until they learned more about what temperature really was. The first law, energy cannot be created or destroyed. So I already applied this earlier when I said we can't create or destroy energy. We can only shift it from one type to another. The second law, heat naturally flows from a hotter material to a colder one. So if I touch a piece of ice, heat flows out of my body. And I feel that. It feels cold. If I touch a stovetop that's on, heat flows into my body because the stovetop is hotter. And I feel that too. The third law says nothing can reach absolute zero. So there's a minimum temperature. Nothing can go below that. And so we have temperature scales. We have the Fahrenheit scale, that has 32 degrees Fahrenheit is freezing water, and 212 degrees Fahrenheit is boiling water. Then we have the Celsius scale, which has 0 degrees Celsius is freezing water and 100 degrees Celsius is boiling water. And then we have the Kelvin scale. I actually should change my color there. The Kelvin scale is an absolute scale that has temperature Celsius plus 273.15. And the reason for that is so the kelvins, 0 kelvins is absolute zero. And so 273.15 kelvins is 0 Celsius. Or you could reverse that. Absolute zero is minus 273.15 Celsius. So make sure that you are somewhat familiar with those temperature scales. If you add heat, something will increase in temperature. And we have M here is just the mass of my object. C is what we call the specific heat capacity. And delta T is the change in temperature. So water has a very high, relative to other materials, specific heat capacity. And so that means if I put a huge amount of heat into water, because C is high, delta T is going to be much smaller than it would be for other things. So water naturally keeps temperatures from fluctuating a lot. So if you live next to a big body of water, like an ocean, your temperatures don't change nearly as much as they will if you're, some miles inland from that body of water. So right now, my sister lives in Huntington Beach, and it's one of the few beaches that's open in Southern California. And so people are flocking to the beach, even though they have all the parking closed off, because near the ocean, the temperature isn't going to fluctuate a lot. So it's been hot this week in Southern California, but at the beach, it's not so hot. It's very comfortable. And so people are coming to the beach to cool off because of the high specific heat of water. If you change phase means going from like liquid to solid or solid to liquid or liquid to gas. You don't change temperature when you put in heat. That energy goes into breaking them free. So changing phase is a constant temperature, and we had a different equation. I don't think we used it in this class. But Q equals ml, where m is the mass that changes phase. And L is called the latent heat. Thermal expansion, because as temperature increases, molecules move faster, they bounce off each other harder and they tend to spread out. So you have an increase in length when you have an increase in temperature. Alpha here is the coefficient of thermal expansion, and it's going to be different for different materials, just like the specific heat capacity is different for different materials. So the general rule is if you put in heat, it should expand. Obvious violation of this rule, water below 4 degrees Celsius. If you have water that's below 4 degrees Celsius and you add heat, it contracts. Or if you take away heat, it expands. This is a real problem because when water gets cold, it can break your pipes. So we have to be careful in places like Lincoln where it gets cold in the winter, or here in Colorado where it gets cold in the winter, because that thermal expansion of the water, doing the opposite of what everything else does, can cause it to break pipes. Okay, we only got 2 more chapters left. Make sure you understand these 3 different mechanisms for heating. Conduction is direct contact. Convection is when you have an intermediary like air blowing, hot air blowing, cold air blowing. Radiation is electromagnetic waves like light. Like I put the E in the end of air instead of the end of like. And conduction was direct contact. So if you touch a candle, you're going to get heating from conduction. If you hold your hand above the flame, you'll get heating from convection. Hot air expands, and because it expands, it's less dense, and because it's less dense, it floats up. If you put it over to the side, you'll get heating from radiation. The greenhouse effect. We did a whole lab on the greenhouse effect. The basic rules for the greenhouse effect is you have a layer. In a greenhouse, it's glass. In the atmosphere, it's greenhouse gases like water vapor. And they allow visible light. I'll use blue for visible light. They allow visible light to go through. But infrared light gets absorbed. And so some of it comes back down, some of it gets re-emitted upward. And so that infrared light gets largely trapped inside, whereas the ultraviolet and visible light comes in. And so you trap energy in, causing the temperature to go up until the amount that escapes equals the amount that comes in. I've already talked about unique features of water, the fact that it expands when it freezes instead of contracting. That's important to sustaining life on Earth, because if it went the other way, water that freezes, the ice would sink to the bottom of lakes, and the lakes would freeze entirely. That wouldn't be very good for us. So that's an important aspect for life on Earth. And then there's the fact of it helping to moderate temperature fluctuations so we don't have crazy fluctuations. The atmosphere also plays a big role in distributing heat around the globe and keeping us from having dramatic temperature fluctuations. The periodic table is supposed to be in the chemistry section. That wasn't supposed to be in this lecture. It's in the next one. So this is the last slide. Electricity. Now remember, we did the lab with static electricity. We learned about Coulomb's law. We had two types of charge, positive and negative, and we have opposites attract. The force law is K, a constant, charge 1. Notice Q is now charge where it was heat in the last chapter, over the separation squared. It looks just like the gravitational force, in fact. The difference between gravitational force and electric force is gravitational force affects everything because everything has mass. Electric force only affects charged objects, and while gravitational force is always attractive, electric force is attractive if you have opposite charges, but it's repulsive if they're the same. So two positive charges will push away, whereas a positive and negative will attract. So electric charge is an inherent property that things have. And remember, protons have a plus E charge. Electrons have a minus E charge. And neutrons, based on their name, have a zero charge. So neutrons aren't affected at all by the electric charge. Only protons and electrons are. Voltage is the energy per charge. So voltage is equal to energy per charge. Current is the rate at which charge is flowing. So it's how fast the charge is flowing. So if we talk about electric circuits in our house, we have 110 volts is equal to 110. Now let's talk about units. The units for energy are joules. I didn't talk about those earlier, but we have the units you should know. You should know mass has a base unit of a kilogram. Time has a base unit of seconds. Position has a base unit of meters. Charge has a base unit of coulombs. And then we have all of these derived units. And so we have energy is, remember we had the equation, kinetic energy is 1/2 mv squared. So that's going to be units of kilograms times meters per second quantity squared. And we call that a joule. So volt is a joule per coulomb because energy over charge. Current is charge per time. So the current, let's say we have 15 amps, that should be about the most current we have. That's 15 coulombs per second. And I don't remember if we did Ohm's law or not, but I'm going to write it anyway. Ohm's law says if I have a resistor, the energy difference from one side of the resistor to the other So delta V, the energy difference per charge, is the rate at which charge is flowing through the current multiplied by the resistance of the resistor. Okay, that is a quick summary of the physics section of the final exam. We'll be back next lecture for the chemistry section, and that'll be the next last lecture.